And next we have self-supervised learning of audio representations from audiovisual data using spatial alignment by Shanshan and Wang.
Yeah, hello. Yes, thanks. Hello, my name is Shanshan from Tampere University, Finland. Today I'm going to present our work, self-supervised learning of audio representations from audio-visual data using spatial alignment. Okay, the title is quite a bit long, and let's get started. So here is the problems we are trying to solve. We are trying to design a pretest task called audio-visual spatial alignment using self-supervised learning method and learning from this 360 degree video and ambisonics. This dataset is called YouTube 360. And eventually we want to learn better audio and video embeddings, feature embeddings. So okay, I will just walk through a little bit about the ambisonics because it's a vision community. I guess everybody is familiar with this 360 video to the plain image, how to convert. But for the ambisonics, I'll just introduce a little bit. So when we talk about ambisonics, normally we refer to first order ambisonics having 4 channels AC and in ACN order, W, Y, Z, X. So W means it's omnidirectional, and X is front, back, and Y is left. Y is left, right, and Z is upside down. So it's just like having 4 microphones and recording all those sound. And it has very nice property. It can rotate because there's a nice rotation matrix. We will not go through the mathematics here, but we can know like how you rotate your head towards this direction or towards that, up, down. So there's angles you can apply the mathematics to rotate the ambisonics, and of course you can also beamform the ambisonics towards a specific direction. For example, like Thomas just introduced about ambisonics, you can beamform it to given a certain direction, then you get the sound what you want. Also using the mathematics transfer this matrix. We will not go through the math again. Yes, so here's our proposed method. Given this 360 video, of course it's not 360 here, just a plain image, and also its corresponding audio ambisonics. And we first apply object detection method using YOLO. For example, here we detect the bird. Then also we from the bird, we have the direction. Then we beamform this ambisonics towards this bird direction to get the corresponding sound. And then we do the 0 steps. Like for image, you do image augmentation. Then for the audio, you do feature extraction to get the log-mail spectrogram and etc. And to train the pretest audio-visual correspondence pretest task. And then get the video embedding and audio embedding. So this is the overall proposed method, and I want to show some examples after applying the YOLO, because normally YOLO works pretty good in the plain video. So I didn't do anything extra to the YOLO method, but it works pretty fine, as you can see, even though those the curves are not curves, not lines, but it works pretty fine to detect all the objects. And also, we also propose a ambisonic spatial feature called intensity vector. So normally what people do is just use there are 4 channels of ambisonics, and then you take the spectrogram of each channel and then stack them. So this is what normally people do, like called log-mail spectrogram. But in this method, we use this intensity vector to capture the spatial features that represents the transfer of energy given a point of direction in the space. And here I will show some experiments. results. So using this intensity vector, we can see from the second column, AVSA task, this in-domain task. The baseline is 71%, but using this intensity vector that represents the spatial features, we get 81%, which is like 10%. I couldn't believe. I don't know whether still how it works, but yeah, this is how the number shows. Yeah, and also from another downstream task, action recognition task, if we can see the baseline for the without fine tuning for the UCF dataset is 36, and using this beam forming plus YOLO to create a strong correspondence between object and also sound, we get 40, like 4% improve, which is also nice. Also, okay, finally, this is the conclusion part. So we propose to create strong correspondence between object and sound using YOLO and plus beamforming. And finally, we also make full use of this rich spatial features of ambisonics intensity vector to improve the representation features. Okay, thank you.